Okay, before we get back into, remember, we're in the middle of an example problem that had to do with moment of inertia, mass moment of inertia, about a point. And that's all finishing up. We're heading towards rotational Newton's second law. But before we get back into all that stuff, I want to talk a little bit about the problem set that I gave you. Has everyone looked at that? Okay. So the point of this problem set, and so as far as the due date, I said if people can get it to me by Thursday, that would be great for me. Anybody who wants to hang on to it, you're welcome to. But the idea of the problem set, so approximately due Thursday. The idea of the problem set is to identify, be guided towards identifying what are the things that make each of these different coordinate systems useful. Like, what are the things that would make you say, I'm going to try to approach this problem with polar coordinates, or I'm going to try to approach this problem using the chain rule in a fixed coordinate system. And I think that's a really useful thing to have, like when you're actually trying to solve a problem that's been designed due to research or whatever, or some product you're trying to design. Obviously, the technique that you use isn't given to you the way it tends to be in a class. So you need to kind of wrap your head around what are the benefits of this, what are the drawbacks of this, when is this technique useful. And so I have a handout here. I'd like you to break up into groups of 2 or 3, go through this worksheet and see if you can make sense out of these questions. It's basically, it's 4 descriptions of motion, 4 kind of mathematical problems defining a motion, and you're asked to, you don't have to do the calculation, but the idea is you're asked to find the acceleration vector. And the question is, in each case, what techniques are worth trying and why? Try to think and talk to each other about why in each case the technique that you're using makes sense. Okay. I do want to give you one heads up. So here's something to get you started on the problem set if you're having trouble getting going. So first of all, you don't have to come up with a real world physics problem that would create this kind of motion. Like, you don't have to say there's a ball attached to a string and the string's being wound. Any kind of mathematical description of motion is fine. So you can define velocity vectors as functions of time, position vectors as functions of time, position vectors as function of x, and you don't have to come up with a connection to a real thing, okay? So that makes it sound kind of easy, but it turns out it's not really. Like, you have to sort of understand what are the benefits of each of these different methods to do it. So to get you started, on number 1, remember, you have to come up with a motion that you can calculate using a polar coordinate system and a fixed coordinate system. So what do you need in order to calculate the acceleration of a motion in a fixed coordinate system? What do you want ideally? You want position or velocity, either one, as a function of, this is sort of the key. Actually, it's easiest, so if you're going to use the chain rule, you're going to need it as a function of some kind of position, okay? But if you just are going to use a fixed coordinate system and take the time derivatives, you just want them as a function of time, okay? So something like, so for a fixed coordinate system, if you have a motion defined like this, you know, something like that, it's pretty easy to come up with the acceleration vector. You're just taking two derivatives, okay? So did I just give you an answer for number one? Well, that would be a pretty horrible thing to try to deal with in polar coordinates, okay? So what are the attributes of something that you'd want to define in polar coordinates? Circular motion is one. Basically anything where it's easy to define r as a function of t and theta as a function of t. Okay. So what you should do for number one is define your motion with r and theta as functions of time. Okay. And then you can just define your position vector as r cosine theta and r sine theta. Okay. So for this one, and what this does is it gives you something that's easy to calculate in polar. And then because these are functions of time, it gives you position also as a function of time. And from there, it's just doing the derivatives, doing the calculations, comparing the points. Okay. Number two is going to be a little trickier, but I think hopefully this exercise will sort of help get you on the right path. So get into groups of 2 or 3. I'm going to make you choose your groups before you get this, because otherwise you'd be like, you know, I'm getting with Ryan, he's super good at this. Or like, oh, dang, I got with Ryan and he sucks at this, you know. So let's go through these one by one. The first one, the problem was you have y of x is equal to 5x squared, and the speed is constant at 3 meters per second. And you need to calculate the acceleration vector. So what are the things that give away? These are exactly the two top choices I would hope you would come up with. What gave that away? So what I'm looking for here is that you don't have a time in there. Everything's a function of position, okay? So you're going to use the chain rule or tangential normal because the only independent variable you know is a position variable. Okay, so let's think about how we would do this in each way. So if you're going to use the chain rule, you have a position vector that's equal to x 5x squared. And you could calculate the velocity as a function of x as 1 over, this all has to do with that using the slope and coming up with a unit vector in the direction of that slope line, that tangent line. I don't really thinking of this as a formula that you plug into is the way to go, but if you do this derivation, you get something that looks like this. That's your velocity vector. And now you can use that the acceleration is equal to dv dx dx dt. Okay. This gets a little ugly, and that's why you're going to see that the tangential normal approach would save you a little time, you know. Either one of these is fine, though. I mean, like when you're working on an actual problem you care about for research or for whatever else, whether it takes an extra 5 minutes or 2 hours or half a day to do a problem doesn't really end up mattering in the overall scheme of things. It's really just whether you can be confident about your answer. So the tangential and normal components. We know that the acceleration vector is the time derivative of the speed in the tangential direction plus v squared over rho in the normal direction. This is 0 because we have a constant speed. Okay, so that makes this problem easy. And that's one thing to look for. Once you've narrowed it down to these two options, if you have a constant speed, the tangential normal coordinate system is often going to be a really simple way to go. Okay, 1 over rho is equal to y double prime over 1 plus y prime squared to the 3/2, which is 10 over 1 plus 100x squared to the 3/2. And so the acceleration vector is, you end up getting 90 over 1 plus 100 x squared to the 3/2 in the normal direction. That calculation, you can imagine, is, you know, a bit simpler than calculating the derivative of this crazy thing with the square root and the, you know. Any questions about that? Okay, the second one. So it starts off the same. You have y as a function of x. But if you can just substitute something in that gives you y as a function of t, then you're set. So our position vector is x of t, and then y of x of t. So 3t, 45t squared. Then it's just taking time derivatives. That one's really easy. There's not even close to a benefit to thinking of that any other way. Okay. The third one, you have the velocity vector as a function of position. Using the chain rule, this is really easy. The acceleration vector is dv dx times dx dt, and that's dv dx times the x component of the velocity vector, which you have. So 2x negative 1 times x squared, and you're done with that one. For all of these, you know, like I didn't give a point to evaluate these, but the presumption then is that whatever point you're evaluating, you'd have as a function of x, just plug it in, x is equal to 5 or whatever, and it gives you that acceleration vector.
You want the values at a certain time.
Mm-hmm.
What would be the best way?
You'd have to know something about a position at a certain time. And that's not just like a limitation of this method. That's an absolute mathematical fact. Like, you can't connect position and time if you don't have any, you know. Okay, and the last one, it's a circular motion. With a radius of 5 meters, and the speed's increasing 3 meters per second every 5 seconds. Okay, so for circular motion problems, thinking in terms of polar coordinates is always a good start. And you could do this in polar. It wouldn't be too terrible. But figuring out what to do with this speed increase in polar coordinates would get a little messy. You'd have to do a bit of thinking. If you recognize that this is saying that the time derivative of the speed is 3 meters per second every 5 seconds, so 0.6 meters per second squared, then you can just treat this as the acceleration is 0.6 in the tangential direction plus v squared over rho in the normal direction. What do we do with that 1 over rho? Well, what do we do with the v? We know that v dot is equal to 0.6. Where the speed at 0 is equal to 0. So that's an easy differential equation, and it gives you that the speed as a function of time is equal to 0.6t. What's rho for a circle? Yeah, right. Rho is the radius of curvature. And for a circle, the radius of curvature is the actual radius. If you remember the radius of curvature, the definition of it is like you fit an infinitesimal piece of that curve to a circle and figure out where that circle's center is. So if the curve is a circle, then those match up. And so the acceleration vector is 0.6 in the tangential direction plus 0.36 t squared, that's v squared, over 5 in the normal direction. Any questions about that one? So that exercise is really about the same thing that this problem set is about, identifying what are the attributes that make something easy in each of these methods. Yep.
We had a v equal to 0.6t. What we get the 0.26t squared?
That's v squared. Just so 0.36 and t squared. Okay. Yep. Yes, that's right. That's right. I made each of these sort of aim you in one direction was my intention, you know. But I mean, I think there's a reason that I grouped these the way I did in the problem set, you know. Like if I had asked you to come up with one that works well in a fixed coordinate system without the chain rule, and then in tangential normal components, that would have been that would have been a big job because those just don't, those aren't the same things aren't helpful for those two methods. You'd have to come up with a function that defined the path based on some parameterization so you could come up with the radius of curvature. It would be a nightmare, you know. But I mean, I think the starting point of thinking about this is if you have something expressed as a function of position, you kind of have two ways to go, the tangential normal or the chain rule, okay? And I didn't put anything with polar that to me worked best with polar because that's usually pretty easy to identify. And you guys who, you know, there are certain motions that just lend themselves to polar, and circular is one of them. Really anything, so to use polar coordinates for something, you're just looking for something that you can define the radius and the angle theta as a function of time easily. That's the only thing that makes that useful. Okay, so any other questions? Okay. I hope that helps you sort of see what you're trying to look for with this problem set.
Theta on that be 0 at time 0?
Theta, if you're so you're trying to express this in polar coordinates? Yeah, you don't know. Nothing gives you, so if all you have is, like, think of it this way, you know some sort of velocity information, right? You know speed information. In order to get position information, you need to integrate that, right? You need to integrate velocity. And so there's a constant of integration that you always need in going from speed information to position. If you're not given it, you can't recreate it, you know, so there's just some indeterminacy there. Any other questions? Okay, so let's go back to this example that we were doing last time. And we were given the density and the thickness. The thickness is 0.2 meters. The density is 3,000 kilograms per cubic meter. And we were given two axes. One was this one, that's the axis A. And then the other one comes out this way. That's the axis B. Okay. So we calculated the moment of inertia about the axis A. Now we want to calculate the moment of inertia about B. Why would we have to do that? When would that be necessary? Yeah, exactly. It just has to do with what kind of spin you're calculating. So if you had a problem where this had a hinge here, okay, then you'd have to calculate the moment of inertia about this axis B. Also, when you do three-dimensional problems, you're going to need to calculate these moment of inertia values for each of the three coordinate axes. That the moment of inertia turns into a matrix in 3D. Okay, so we're going to use the same approach we used last time. We're going to calculate the moment of inertia of the rectangle about B, calculate the moment of inertia of the disk about B, and then we're going to subtract. Okay? And so I'll call this axis C, and I'll call this axis going through the center of the rectangle R. Okay? What are the purposes of those two axes? Yeah, right. So these are the axes that go through the center of each of these two objects in turn that are parallel to the axis that we want. Okay? So first I'll go moment of inertia of the rectangle about R. That's 1/12 times the mass of the rectangle times x squared plus y squared, or actually I think L squared plus W squared is what I call it. The mass of the rectangle is 4 times 2 times the thickness times the density. We did that last time. What do you get for that? Can someone calculate that? I don't have it written down. 800?
48.
Okay, so the moment of inertia is 4,800 divided by 12 times 4 squared plus 2 squared and so you get what's that, 400 times 20, 8,000. What are the units for moment of inertia? Kilogram meter squared, yep. And now we want the moment of inertia of the rectangle about B. So we use the parallel axis theorem. So 8,000 plus 4,800 times the distance squared. What's the distance? We're going from R, the center of the rectangle, to here, so the distance is 2 meters. So 8,000 plus 4 times 4,800. What do you get there? Okay, kilogram meter squared. So we'll come back to this. Now we want the moment of inertia of the disk. Oh, was that 27? 200? Okay. So now the moment of inertia of the disk about C for circle now we need to think about this for a second. Well, once you've drawn it in here, this isn't a bad way to do it, actually. If you draw the axis in that's parallel to the axis you want, it sort of makes it easier to visualize what axis you need to do this calculation about. If this C axis wasn't drawn in there, it can be a little tricky to figure out, am I looking for a rotation about as the disk spins around its side, or like a wheel? Okay. But in this case, we want the moment of inertia for the disk spinning like a wheel, okay, because that's the axis that's parallel to B. So mr squared over 2, the mass of the disk is pi, the radius is 0.5, so pi r squared times the thickness times the density. What do you get there? Okay. And so the moment of inertia is 471.2 times the radius squared, 0.5 squared divided by 2. What do you get there? Okay. And so now we have to use the parallel axis theorem. The moment of inertia of the disk about B is 58.9 plus the mass, 471.2, times the distance squared. So what's the distance between C and B? 2 and then a half, right? So 2.5 meters. What do you get there? Okay. And so finally, the moment of inertia of the whole shape about B something went wrong. Oh, no. Okay. No. 27,200 minus 3,003.9. And so what do you get? Okay. Kilogram meter squared. Okay. Any questions about that? For the other axis, for that A axis, we got 22,625. It's one radius from the bottom, so it's 2 meters to here, and then just one radius. The whole thing is 1 meter tall. Okay. So now that we're done with, we've talked about angular acceleration, we've talked about moments, we've talked about moment of inertia. So So now we can talk about rotational Newton's second law. And the definition of rotational Newton's second law is the moment vector, the total moment vector on the body is equal to the moment of inertia times the angular acceleration. Notice that the moment and the moment of inertia have to be defined about a point, and those points have to be the same. And that's not the only restriction. A has to be either fixed on the body and fixed in the coordinate system, or B has to be at the body's center of mass. If A is any other point, then this equation isn't true. Another way to think of this is the moment about the center of mass is equal to the moment of inertia about the center of mass times alpha, always. And MA equals IA times alpha when the point A is fixed on the body and fixed in the coordinate system. And what about this angular acceleration? How do the angular accelerations between, so say for example, you had a body, you had your choice of these two. Anytime you have a body that has, where a point on the body is fixed in your coordinate system, like at a pin joint or something, then you have two options for doing this problem. You can always do it at the center of mass. You also, in that case, can do it with A at the pin joint. Then how do these angular accelerations relate? Actually, they're the same thing, okay? And so think of angular acceleration, angular velocity. Those are properties of the body that don't have anything to do with any about point or anything like that, okay? They're just how quickly, like how much orientations of the body are changing, okay? So the angular acceleration doesn't care if the body's moving around a big circle like this, or if it's in space just doing this. It only matters how its orientation is changing. And that's the same for both of those. Okay, so notice, this is important. This is going to be sort of a key to using these things, especially when we start talking about linkages, like robotics type stuff, where a bunch of bodies are connected by joints. Rn2L has two close companions that are going to come up in almost every problem. The first one is Newton's second law. And for rigid bodies, remember that says the total external force is equal to the mass of the body times the acceleration of the body's center of mass. And second, the acceleration of a point is equal to the angular acceleration crossed with the r vector plus omega cross quantity omega cross r. This is the equation, the vector version of the equation that gives you the acceleration for circular motion. Okay, so I have a question. If rotational Newton's second law always works for the center of mass, why not just simplify our task and just always use that? So what would you guess the answer is? Is that true, first of all? Like, am I misunderstanding something?
Objects of different material.
Well, actually, so sometimes you do use that approach. But the calculations are a lot simpler when you can do the calculation about a fixed axis. Or using a fixed point. Okay, so when do you use this approach? A lot of times if you're writing a computer program to do these calculations, you don't want to have like separate cases, have to figure out whether there's a fixed axis or whatever. And the computer does all these, even if the calculations get complicated, the computer does all those instantly, so you don't really care about that. So often in computer programs, you will just always do your calculations about the center of mass. We're not doing that in this class, though. So for us, since we're going to be doing everything by hand, we're going to want to take advantage of the fact that, you know, some problems are going to have a fixed axis. It's going to save you a lot of work. And the next example I'm going to do is we're going to do a problem both ways and see where the complications come in. Okay. So what makes it simpler when you know a fixed axis? Using the center of mass, when you have a fixed axis or a fixed point, requires finding another geometric constraint. Constraint equation. And that constraint equation isn't as simple as some of the ones that we've seen so far. Like if you're working with pulleys or something, you often have sort of simple constraint equations, just saying the acceleration here is negative of the acceleration here or whatever. These constraint equations are going to use the relative motion equations. And they're also going to use that circular motion equation. Okay, so let's do this as an example problem. I'm going to draw this picture. Imagine it being a view from above, so we're not going to deal with gravity or anything in the plane that we're doing this calculation. Okay, so say that you have this plank, and it's rotating about a pin. So it can spin freely about this point. The center of mass is here. The whole thing has a length of 1 meter. This is at the midpoint. This is half of the way between the midpoint and the end. This distance is 0.2 meters. And let's say that this plank has a mass of 30 kilograms. This angle is 30 degrees. And at this instant, this object's rotating with an angular velocity of negative 15 radians per second. And say that there is a force at the midpoint here between the center and the end of 100 newtons. And we want to calculate the angular acceleration vector using the fact that there is one of these fixed points. Okay, there's a point that's fixed on the body. Its location in the body isn't moving, right? And it's also fixed in our coordinate system, the coordinate system we're going to choose. And then we're also going to calculate it using our about point as the center of mass. Any questions about this problem? Okay, so if we're going to start with the fixed point, doing it about the fixed point. We know we're going to use rotational Newton's second law, so at some point we're going to have to calculate the moment of inertia. So the moment of inertia, first we'll calculate it about the center of mass, and then we'll use the parallel axis theorem to move it here. So it's 1/12 times the mass times the length squared plus the width squared. (2.6 kilogram meters squared). And now about that fixed axis, it's 2.6 plus the mass times the distance squared. What's the distance? Yep, 0.25. And so you get a moment of inertia of 4.475 kilogram meters squared. And now we have to calculate the moment. We only have that one force. Well, we have, I'm getting ahead of myself. So let's draw the free body diagram. Okay, so there's the body. Where are their forces? There would be mg, except that I said this is a view from above, so that's just not appearing in this problem. There's this force, right, the one we're applying, but there's also one other force at the pin, right? If there wasn't a force at the pin, this thing wouldn't, it would just translate off into space. So there's also a force vector here. So this one's 100, and this one, do we know anything about the direction of this force? Right, not without using Newton's second law. You can sort of have an idea, do Newton's second law in your head and recognize it's the opposite direction of this, but we'll just write it like F. Okay, we're calculating the moment about that fixed point A, right? So that force F that we don't know isn't going to produce any moment, okay? And that's the first big simplification you get when you have a fixed point. You have an unknown force in almost every case that has to be calculated in the moment when you're using the center of mass, and it doesn't have to be calculated in the moment when you're using the fixed point, okay? That's a nice advantage. You can probably recognize that just this is a perpendicular force, so this 100 times this distance of 0.5 is going to give us the moment. Let's set it up like the table, okay? Because it takes more time, and who doesn't want to spend more time? Okay, so because this is the way to do this calculation when there's no simple way to do it, or there's not necessarily a simple way to do it. Just set it up, calculate the vectors. It can be a little tedious, but it'll always get you the right answer. So professional aquanauts row for money. Yeah, I'm full of them. I don't even remember that one. Row for marzipan. Yeah. And now we're just going to go force by force. So let's first deal with the force here. I guess we have to choose where our coordinate system origin is. Let's put it here. Okay. So if we're doing the force that's at that pin, the location where that force is applied is at the origin. I'm going to write these all as three-dimensional vectors because the moment is going to come out in the z direction for a plane problem. The about point is also at the origin because that's the fixed point. You can move the coordinate system, so you could, which would change the value of p, but we can't move this a. That's at that fixed point or at the center of mass, depending on whatever you chose. Subtract these two and you get zeros. Our force vector has an x and a y component, but no z component. And so now the cross product in a plane problem, a 2D problem, which is the vast majority of what we're going to be doing in this class, it's this times this minus this times this. And so you get a moment of 0, 0, 0. Okay. Now how about that 100 Newton force? You can move any of these forces along their line of action without changing the problem once you've decided what you're going to call a rigid body. So let's just move it to here to make it a little simpler. We know that this angle's 30 degrees. So and this distance is 0.5. So we have the position is negative 0.5 times the sine of 30, negative 0.5 times the cosine of 30. Does that seem right? And then 0. And so let's, so 0.5 times the sine of 30 is 0.25. 0.5 times the cosine of 30 is 0.433. Okay, so that's just geometry, figuring out the coordinates of that point. The about point, that doesn't change. So all these forces have to have the same about point. So all the way down this line, if there's 100 forces, they all have the same value in A. This is 0, 0, 0, representing that fixed point. And so this time the row vector is this minus this 0, this minus 0. So negative 0.25, negative 0.433. The force vector is, I'm going to go with negative 86.6, positive 50. If this angle's 30. So take the cross product. We have negative 1/4 of 50. This is going to be in the z direction. So negative, what's that, 12.5? And then minus 0.433 minus times 86.6. What do you get there? $37.5. I think it should be. Is that right? For the, yeah, so the whole thing is negative 50, right? Which is what you would have gotten if you would have just done the simplified problem. Recognize that this is a perpendicular force times a moment arm of 1/2 meter. Okay, so the nice thing about this table, I mean, there's a few nice things. It just sort of systematizes things. Now, if you're going to use Newton's second law, you go straight down this column, adding those up. And that's your left-hand side of Newton's second law. And if you're going to use rotational Newton's second law, you just go straight down this column, add those up, and that's the left side of the rotational Newton's second law. So rotational Newton's second law now says, add these up, you get 0, 0, negative 50 is equal to, the moment of inertia is 4.475 times the alpha vector. And so the angular acceleration is 0, 0, negative 11.1732 radians per second squared. So in the, looking at it from the view that I've drawn here, is that clockwise or counterclockwise? it's in the negative z direction, so it's clockwise. Positive is counterclockwise. Okay? And you can do it with the right-hand rule. This is in the, it's in the negative z direction, which is down, right? So your fingers are going clockwise. Okay, so next time, same problem using the center of mass. We're going to see why the first method is simpler when you have the choice. And we better get the same answer for the angular acceleration, because like I said, you know, that's a property of the body. That doesn't have anything to do with what about point you choose. Okay. All right, that's it. And yeah, feel free to come by if you have questions about the problem set.